Hello viewers, I welcome you all to my own YouTube channel. This is a video lecture on inorganic chemistry, which is we are going to study today P block. Actually, we are starting a new lecture series on the P block elements. Today we will see about the group 13 elements. So if you like the video, please share and subscribe my channel for latest videos. So we are starting P block group number 13. So in group number 13, there are boron, aluminium, gallium, indium, thallium. So these are the elements which are present in group number 13. Or you can say this is group number 13, or you can say 3A. Now, what happens? Whenever we have to study any specific type of elements, we have to see their occurrence and their reactions and their properties. So at first we have to know their occurrence. Actually, boron is generally found in borax. It is found in borax Na2B4O7.10H2O, or it can also find in Na2B4O7.5H2O. It is known as Mohavite. Okay, or it can also be found as in Ca2B6O11.5H2O. It is known as colemanite, or you can also find in Ca2B6O11.4H2O. So boron can be found in these kinds of elements, which are really important in the preparation of boron, in the production of boron, and they are found in different ways. Boron can be found in borax, mohavite, colemanite, etc. Aluminium, actually, this is more abundant in the earth crust. Actually, this is the third element, the third most abundant element in the earth crust. Actually, aluminum is found generally in Al2O3 dot twice H2O. This is bauxite. Gallium occurs in traces in bauxite. We can find out 1 by 5,000 part of of gallium in bauxite. Indium and thallium, they are found in flue dust. Flue dust actually is an industrial waste, and it can contain a variety of elements in it. So these are the occurrence actually. Boron is found in borax or mohavite or colemanite. Aluminium is found in case of uh, bauxite, and is also the third most abundant element present in the earth crust. And gallium occur in traces, okay, in bauxite, has 1 by 5,000 part, and indium and thallium generally occur in the flue dust. So these are their occurrence of the group 3 elements. now now you should see the structure of borax. Actually, the structure of borax is more important for your entrance examination. So borax Na2B4O7, okay, so dot 10H2O. Okay, so this is the structure of borax. Actually, here this boron have excess valency 1, 2, 3, and 4. So this will be a coordinate bond. Now overall the charge is -2, so you should satisfied by it to sodium plus. That's why the structure is, that's why the formula is Na2B4O7. Now the question that comes in the entrance examination, how many BOB bonds are present in borax? So you should remember the structure of borax, then you can easily give the answer. So what happens, we should go through their physical properties first, then we should discuss their chemical properties. Now in group 13 you can see in group 13, first their melting point comes. So this is boron, this is aluminium, this is gallium, this is thallium, this is indium, and this is cellium. Okay, boron has a very high melting point. Actually, you can see that boron exists in two forms, crystalline and powder form. So the crystalline form is ultra pure in nature. The powder is about 95 to 98% purified. It can contain some impurities also. The melting point is very high. Approximately, you can say that the melting point is 2300 degrees centigrade. The melting point is 2300 degrees centigrade. Aluminium, you can see there's a drastic change in the melting point. You can see the melting point is 600 degrees centigrade. Okay, I'll explain. Gallium, it has a melting point of it has a melting point of 30 degrees centigrade. Generally, indium and thallium are less important for our entrance and our board. That's why we should not discuss greatly in this case. So you can see the melting point is approximately 700 degrees centigrade. So these are the melting points. So we should just focus on these two elements. These two elements. What happens? The size of boron is very small, and what happens, it exists as it exists as a giant polymeric form, which is known as the icosahedron structure. So a large amount of energy is needed to break this, or to melt the molecule, giant size molecule, because it does not exist in a single atom. It exists in a giant polymeric structure. That's why we should need a high amount of energy to break this kind of bond. That's why boron has a higher melting point, approximately at 2300 degrees centigrade. There is a drastic change in the melting point from boron to aluminium. This happens because actually the size of aluminium increases from boron. That's why the drastic change is there. Aluminium has a melting point of 600 degrees centigrade. It can show some metallic properties. Okay. Okay. So this is the melting point of aluminium. Gallium, it occurs in a diatomic form. Okay, diatomic form. So gallium in the room temperature is liquid in nature, so it has a melting point of 30 degrees centigrade. So the drastic change from boron to aluminum occurs due to the increase in size, and the size increases rapidly. That's why the melting point behaves like this. Gallium is a diatomic molecule. That's why it will show a lower melting point. Okay. So the melting point of group 13 elements does not follow the trend. Okay, they should be irregular in nature. So this is the melting point. Now we are going to the oxidation state. What happens in case of oxidation state? The electronic configuration of group 13 is ns2 np1. So you can see the electronic configuration is like that. Okay, like that. Now what happens? It should show it should show a valency of 1, but they show valency of 3. This is because what happens, one electron is transferred from here to here. This is actually what happens whenever you excite one electron from the ns orbital to the np orbital. Some amount of energy is needed, so the atom becomes unstable in nature. But what happens, this is the reason why the electron is jumping from ns to np orbitals. This is the reason, you should note it down, that the amount of energy that is needed to excite the electrons from the ns orbital to the np orbital is easily compensated by the amount of energy released during the formation of additional two bonds. This is the reason why the electron is excited from the ns to np orbital. What happens now? You see, let us assume that we are absorbing 50 electron volt of energy while transferring this electron from this position to this position. What happens? Boron should form one kind of bond. Let's say one bond. Let's uh, make a boron halide. If one electron is in the unpaired condition, then the boron halide should have a formula of BCl. But actually, this is BCl3. What happens? The amount of energy. Let us assume that 50 electron volt of energy is absorbed during the transfer of one electron from here to here. But what happens during the formation of additional two bonds? Now see, boron should form only one BCl bond, but it forms BCl3. So what happens? These two bonds are additional bonds. So during the production of this kind of bond, let us assume that 70 electron volt of energy has been released from the system. So what happens? The system becomes lower in potential energy and the stability increases. That means the amount of energy that is needed to excite the electron from the ns to np orbital is easily compensated by the amount of energy that is needed to that is needed the amount of energy released during the formation of additional two bonds. So this is the uh, reason why group 13 elements show a valency of 3. Actually actually the stability of plus 3 oxidation state goes on decreasing while going from top to bottom. Now you can see boron, aluminium, gallium, indium, thallium. So the while going from top to bottom, the plus 1 oxidation state is more stable is more stable in case of thallium because due to the due to the inert pair effect. Inert pair effect. Actually, you should be careful here. Inert pair effect. Inert pair effect. Actually, this is shown by the heavy elements in the p block. Now you can see here 13, group number 13, group number 14, and group number 15. There are in group number 13 the element is thallium. Here it is lead. It is bismuth. It should show a valency of 3. It should show a valency of 4. General valency should show a valency of 5. But this shows plus 1, or sorry, valency of 1. This shows a valency of 2. This shows a valency of 3. What happens? The naturally occurring heavy elements present in the p block has a general tendency to show oxidation state or valency decreased by 2 units from their corresponding groups. That means the elements present in these groups will show a valency or oxidation number decreased by 2 units from the normal valency. You can see that thallium is present in group 13. The maximum elements present in the group 13 shows a valency of 3, but thallium shows a 1. The question comes in the examination that TlCl3 is a very good oxidizing agent. This is because here the oxidation number is plus 3, but thallium is stable in plus 1. So it is wanting to get reduced, and it will act as an oxidizing agent. This is very simple actually. Thallium is present in plus 3 in case of TlCl3, but thallium is stable in plus 1. So it want to decrease its oxidation number from plus 3 to plus 1 to become more stable. So it will get reduced and it will act as a strong oxidizing agent. So these are the this is the inert pair effect. Now you can see actually now you can see boron never show plus 3 electrovalency. It shows a plus 3 covalency. Means you cannot see that boron 3 plus is present here. You can see that in case of BCl3 or BF3, you can see the valence oxidation number is plus 3, but you will not find it in the ionic form. Not in the solution phase also, not in the solution phase also, boron will give plus 3 electrovalency. But the rest of the elements, but the rest of the elements can show plus 3 electrovalency in the solution phase. Okay. Now see here, such as NaAl, H2O whole 6, Na3, sodium metaluminate. Now you can see that here it exerts the oxidation number of plus 3. Okay, now you can also write it down like that. AlH2O whole 6, 3 plus. So these are the uh, it, likewise gallium can also show this kind of property. You can see Na3GaH2O whole 6. Okay. So the tendency to form uh, electrovalencies in the solution phase increases. So while going from top to bottom. So these are the oxidation number. This is the tendency of oxidation number. Actually, now we can move on to the. So we have covered oxidation number. Now number 2 is melting point. Number 3 is ionization energy. So this is ionization energy. Actually, boron has the highest IE1 first ionization energy comparing to rest of the elements present in group 30. This is because boron has a very small amount, very small size and higher electronegativity. What happens here is a abnormality you should see while going from left to right. While going from left to right, the ionization energy one increases generally. It is a general trend. Okay, this is not a hard and fast rule. Why, how high ionization energy will behave, but while going from boron, sorry, beryllium to boron, it should be, it should be, uh, it should be the ionization energy of boron should be higher than beryllium. But actually, this is wrong. Actually, beryllium has a higher ionization energy than boron. This is because there is a very important and a very good explanation about this. This can be written as like that. So the question comes here: why beryllium has a higher ionization energy than boron? What happens? Here you can see that the electronic configuration is NS2 of boron. It's the S block element. Okay, and the electronic sorry of beryllium. The electronic configuration of boron is NS2 NP1. Now you see here. Now you see here the p orbital is in the unstable condition. Unstable condition because it is partially filled. But here the s orbital is full filled. Full filled means higher stability. Fulfilled means higher stability. So it requires a higher energy to eject an electron from the filled ns orbital. Moreover, this is the most important explanation. Moreover, in s block, the orbital is nearer to the nucleus, so it requires a higher amount of energy to eject an electron. This is called a penetration power. Penetration power. Okay, this is called penetration power. S block has a higher penetration power than the P block. That's why the ionization energy, first ionization energy of boron, sorry, of beryllium is higher than that of boron. Now you see here. Now you see boron never shows a +3 electrovalency. Not only this is true that beryllium has a greater ionization energy of boron. This is true. Number one. Number two is that is magnesium. Magnesium is greater than aluminium. Then it is beryllium, magnesium. This is calcium. You can see calcium has a higher ionization energy than gallium. These are the trend. You should remember this. These are the exceptional cases. Boron never show plus 3 electrovalency because the IE1 plus IE2 plus IE3 is very, very high. The summation of I1 plus I2 plus I3 becomes very, very high. So this is, or it is, energetically, okay, impossible. So boron never show plus 3 electrovalency. You should remember this because the summation of the first three ionization energy becomes so large that you cannot eject 3 electrons from boron and it will never show a plus 3 electrovalency. Next one. Okay, the next one. So we have covered up to this melting point. Number 2, oxidation state. Number 3, ionization energy. Now we should see. Now we should see about nature of bonding. Nature of bonding. What happens here? Generally, boron forms covalent bonds. You will not see boron in the ionic form. It will form such as BCl3, BF3, BBr3, Bi3. Now you can also see for forms a different type of compounds, hydrides, clozohydrides, nidohydrides, and arachnohydrides. We should see them in details in the when we read boron particularly, then we will see them. So the nature of bonding is generally in case of boron is covalent in nature. Okay, but such as you can see also AlCl3 in the solid phase, it is also covalent in nature. You can see that GaCl3 is also covalent in nature. But aluminum chloride, you can see it whenever it is dissolved in water. Whenever it is dissolved in water, the hydration enthalpy, the hydration delta H hydration. Okay, hydration enthalpy is 5806, approximately the literature value minus this kilojoule per mole, and the ionization energy is 5104 actually kilojoule per mole. So it can be ionized in plus 3 oxidation state in the solution phase. So this is the nature of bonding of the complexes of the elements in the uh, aqueous phase or in the solid phase. Now we should see some chemical properties. Actually, this is the most important part. Now you can see here chemical properties. While reading the chemical properties, we should see also always the reactivity towards air. Reactivity towards air. Now what happens? Reactivity towards air. What happens? Boron in the crystalline form does not react with air, but when heated, react with oxygen to produce boron anhydride. You can produce this B plus O2. This will produce B2O3. Similarly, Boron in the heated condition produces general properties, chemical properties of group 13, produces boron nitride B plus N2. This will produce Bn, boron nitride. Okay. The polymeric form of boron nitride is called as inorganic graphite. Inorganic graphite. Okay. In the polymeric form, it is known as inorganic graphite. Actually, aluminium also does the same type of reaction. Aluminium also does the same type of reaction. Aluminium does not react with anhydrous air. It requires moist air and it produces Al2O3, which act as a protective layer. So as you can see that aluminium plus oxygen, this will produce Al2O3. Aluminium plus nitrogen, this will produce ALN. So aluminium nitride, aluminium nitride. Actually, this Al2O3 is the most stable. This is the most important star. Star most stable compound of aluminium has a melting point of near about 1800 degrees centigrade to 2000 degrees centigrade. It is highly stable in nature. Okay, this is the reaction. Yeah. Now here we can see. I'm sorry for the net connection. This is very poor. Actually, the net connection is very poor. Sorry about that. The next one we can see reactivity towards acid. Now you can see various types of reactions are possible here. Boron, when reacts with H2SO4, it produces boric acid H3BO3 plus SO2. This is the reaction. Now you see here, aluminium similarly react with H2SO4. It also react with H2SO4. Now you can see in the aqueous condition, you can see here, this produces Al2SO4 whole 3 plus SO2 plus H2O. Now here boron also react with HNO3, B plus HNO3. This will also produce H3BO3 plus NO2. What happens? Aluminium does not react with HNO3 because it produces a protective layer of Al2O3, so which is insoluble in HNO3. That's why, which is Al2O3, Al2O3 is insoluble in HNO3. So this will not show any kind of reaction. Actually, it will form a protective layer. Thallium also reacts with H2SO4, but the reaction is different. You can see here, thallium plus H2SO4, this will produce plus hydrogen will be released. So this thallium act as a metal in this case, as we can see, hydrogen is being liberated from the acid. So this is the general reaction of acids. We'll see them later. Now you can see the properties of oxides and hydroxides. The next point, oxides and hydroxides. Actually, this is actually most important. Now you can see here, boron forms B2O3, boron anhydride. Actually, this B2O3 is responsible for the borax bead test. For the borax bead test. What happens? You should see about this. Now, what happens? Borax bead test is performed in the laboratory to find out some special element. Some amount of Na2B4O7.10H2O is taken in a tip of a platinum wire and heated gently, first gently, and it loses 5 water molecules, Na2B4O7.5H2O. Now you give heat again, this will produce NaBO2. Sorry, now all the H2O molecules will be reduced. Na2B4O7 anhydrous, dry, white mass. Now give heat here, this will produce NaBO2, sodium metaborate plus B2O3. This is a glassy bead. Actually, this is known as sodium metaborate. What happens now? You see here, whenever you do the borax bead test, what happens? You should see here, CuO plus B2O3. This will produce CuBO2 whole 2, copper metaborate, NiO plus B2O3. This gives NiBO2 whole 2 reddish brown, inflamed, cobalt plus B2O3. This will produce COBO2 whole 2, cobalt metaborate. It's a bluish in nature. So this is the borax bead test actually. So B2O3 is acidic in nature, but in some cases, this is actually the most important part of this lecture. Actually, the most important part, B2O3 is acidic in nature, but in some cases, it can show some basic nature, such as I'm writing two reactions. You should remember these reactions, very important reactions. These are B2O3 plus P4O10. This will produce BPO4, boron phosphate. B2O3 plus AS4O10. This will produce BASO4, boron arsenate, boron phosphate. Actually, these reactions are most important. In these reactions, we see that B2O3 can also act as a basic oxide. So B2O3 can act as a basic oxide. But aluminium oxide or Al2O3, alumina, this can act as both Al2O3 plus H2SO4 aqueous. This can, it can also react with Al2SO4 whole 3. This will produce Al2SO4 whole 3 plus SO2 plus H2O. This one reacts with Al2O3 plus sodium hydroxide. This will produce sodium aluminate NaAlO2, okay, plus H2O. So aluminium reacts with H2SO4, aluminium oxide, but aluminium oxide Al2O3 does not react with HNO3. You should see the next one. Actually, Al2O3 does not react with HNO3. Here, you should see B2O3 only reacts with oxidizing agents or strong oxidizing agents such as H2SO4 or H2SO5, etc. Now, these are the general properties of oxides. The next is hydroxides. BOH whole 3. Okay. Now, BOH whole 3, this hydroxide is also called as H3BO3. It is mildly acidic in nature. Mildly acidic in nature, but when we do the standardization of H3BO3 with NaOH, we will not have any sharp neutralization point because this is mildly acidic. This is mildly acidic. Now, you should see here, in presence of glucose or dimanitol, we will find a sharp endpoint. This is because H3BO3 forms a complex with glucose. Now it's able to release H plus easily, so we'll get sharp endpoint. So H3BO3 is actually very weak acid. It occurs in polymeric form. Actually, we will not get any sharp endpoint while we titration. While the titration of sodium hydroxide with sodium hydroxide will get a sharp endpoint whenever it is treated with dimanitol or D-glucose. Then the titration is carried out in presence of phenolphthalein, and you will find out the sharp endpoint of this. The conductometric titration, you should see the conductance will be first decreased, and the increase of dimanitol, the conductance increases, then decreases, then increases, then decreases. So these are the simultaneous simultaneous formation of complexes and breakdown of complexes is responsible of such kind of conductometric titration graph in case of conductometric titration. So this is the explanation why dimanitol, in case of in presence of dimanitol or D-glucose, it will show a very good titration. Now you should see the complex forming tendency. You should see the complex forming tendency. So, okay, no, hydroxide is not over yet. Hydroxides, you see that boron forms uh, BOH whole 3, aluminium forms ALOH whole 3, gallium forms GaOH whole 3, indium forms INOH whole 3, or INOH, helium forms TLOH. Basic nature increases. Now, metallic character is shown by thallium generally. So, inert pair effect plus one oxidation state is stable. So, these are ALOH whole 3 actually is amphoteric in nature. It also reacts with both of the acid and bases. Now, the while going from top to bottom, the basic nature increases. The basic nature increases. Now we will go through hydrides. Okay, this is the hydroxides. Will talk in details whenever we see boron and aluminium separately. Whenever we read boron, the properties of boron and all of its reactions and elements compounds. Whenever we see aluminium, whenever it separately, we'll see the oxide and hydroxides and their some of the different characteristics. Now, what happens in case of hydrides? BH3, borane. Now, ALS3, alane. Now, GH3, this is known as galane. INH3, indane. TLH3, thalane. So, BH3, borane, ALH3, alane, GH3, galane, and INH3, INH3, indane, TLH3, thalane. Actually, the hydrides of boron, the hydrides of boron are of types, different types, generally closo, nido, and arachno type of hydrides are formed by borane. Actually, they can be in the polymeric form also. We are not discussing here the closonido and arachno form, where whenever we study about diborane, then we will see about closonido and arachno form. Actually, the stability of the hydrides decreases. And the thermal stability of the hydrides decreases while going down. You can see that diborane, you can find out diborane as B2H6, not BH3. But aluminum hydrides, alanes, are, are thermally very unstable. It is very difficult to find out them. Okay. The chemistry of these three type of hydrides are very complex in nature. So, uh, there are different kinds of hydrides of boron also. We can see that tetrahydroborates. We can see that NaBH4, sodium borohydride, sodium borohydride. Okay, LiBH4, lithium borohydride. These are also hydrides of boron. These are known as tetrahydroborates. So, okay, why these are called tetrahydroborates? You will write down the IUPAC name: lithium tetrahydroborate 3. This is the uh, IUPAC of lithium tetrahydro LiBH4. Sorry, this is the IUPAC of this is the IUPAC of LiBH4. So these hydrides are actually most important. Actually, you can uh, form some of the hydrides with the help of these kind of hydrides. Okay, actually these are NaBH4 is a mild hydride transfer reducing agent. It is a regio selective reagent which reduce aldehydes and ketones, does not reduce esters and carboxylic acids. Now you can see some reaction here. Now you see, you can write down some inorganic or organic reaction. CH3CHO, it is organic reaction. NaBH4, this will produce CH3CH2OH, or CH3C double bond O single bond CH3 plus NaBH4. This will produce a secondary alcohol CH3CHOH single bond CH3. You should see this, or BCl3 plus. How NaBH4 is formed? Production of preparation of NaBH4 BCl3 plus NaH. This will produce NaBH4 plus NaCl, or you can find out BCl3 plus LiAlH4, lithium aluminium hydride. Lithium aluminium hydride, you can see there, whenever you do the reaction, this will produce Li, uh, okay, LiBH4 plus LiAlCl4. Okay, so these are the reactions. NaBH4 actually, NaBH4 actually, NaBH4 cannot reduce, can't reduce esters. You can see CH3 C double bond O C2H5. Whenever you give NaBH4, it has no reaction. But NaBH4, we'll see in details in the hydrides. NaBH4 presence of in presence of diglyme or triglyme can act as a very good reducing agent, or triglyme, or in 18 crown 6 crown ethers. You see the structure of 18 crown 6. This is the structure. This is the structure of 18 crown 6. Sorry, sorry. Okay, the structure of 18 crown 6. So in presence of some crown ethers, diglyme or triglyme, diglyme or triglyme, diglyme and triglyme, actually they are high boiling ethers. Okay, so this is the uh, property of NaBH4. We'll see the rest of the chapter in three separate parts. The next video will see cover about the rest of the chemical properties of this group, and then we will go through boron and aluminium individually. For today's video, I'm ending the video here. If the video is useful and you can find out some important information in this video, and you should share and like my video, and also click the bell icon for latest notification. Actually, in case of p block elements, the question comes directly from these topics, and I'm discussing on the entrance basis. Actually, these are most important for your entrance examinations such as NEET, JEE, AI. You can see that AI, EEE, JEE mains, IIT, advanced, etc. So you should follow the class sincerely, and if you find it actually informative, then you can share my video, and thanking you again to see the video, and I'm inviting you to watch my next video on p block. So thank you very much.